In section 2.4, we're going to look at exact equations. So although the simple first order differential equation y dx plus x dy is equal to 0, it's not only separable, but it's also linear. So we can solve this either via separation of variables or via using the concept of our integrating factor from the last section. Okay. A new way and an alternative way to solving this is that we might recognize this expression, this y dx plus x dy, as being the differential of the function f of x comma y equals xy. Okay. So if we were to take the differential of xy, this is equal to y dx plus x dy. As kind of a good review from, let's say, like Calculus 3, if you have, let's say, the differential of a function. So if I wanted to take the differential of some function f of x comma y, what this would be the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y dy. This is what we mean by the differential of an expression. So essentially what's happening here, when we look at these differential equations that are presented kind of using the differential notation, we can think of there as being some function, let's call it m, and it's generally going to be of the variables x and y. So we have some function of x and y in front of the dx, we're going to call it m, and similarly the term or the function in front of the dy term, we're going to label that n of x comma y. And then the question is given an expression of this form, is this expression the differential of some function f of x comma y? And if the answer is yes, then we can refine and solve for the original function f of x comma y by using partial integration. Okay. So again, I just highlighted this a moment ago, but if you have a function of f of x y, let's just call it z, its differential dz is equal to the partial of f with respect to x times dx plus the partial of f with respect to y dy. In the special case when f of x comma y is equal to a constant, this would simply be equal to 0. Let's take a look at an example of one of these. Okay, so if we were to look at x squared minus 5xy plus y cubed equals to c, if we were to take the partial derivative of this with respect to x, that would be a 2x minus 5y, which would be times the dx, plus, now we would need to take the partial with respect to y. This term would be 0. This would give us a negative 5x, and then the 3 would come down, we would get 3y squared. That would be times dy, and then of course the differential of a constant, that would be equal to 0. So this brings us to the definition of an exact equation. A differential expression m of x comma y dx plus n of x comma y dy is an exact differential in a region R of the xy plane if it corresponds to the differential of some function f of xy defined in R. A first order differential equation of this form is said to be exact if the left-hand side is an exact differential. So for example, this expression here, x squared y cubed dx plus x cubed y squared dy, this would be an example of an exact differential, of an exact equation, because it is the differential of the function 1/3 x cubed y cubed. In this setup, if we look at the coefficient function for dx, that's the x squared y cubed, we're going to call that m, and the coefficient function for the dy, that's going to be the x cubed y squared. One of the things that we notice is that the answer to whether or not this expression was the differential of some function was yes, and we can kind of observe this by looking at the following criteria. If we were to take the partial of m with respect to y, so if I differentiate this function with respect to y, the 3 would come down, that would be a y squared, we get 3xy squared. Notice that if I then take the partial derivative of n with respect to x, here the 3 would come down, the x would become a power of 2, and that would also provide 3x squared y squared, which is the partial of n with respect to x. And it's the equality of these partials that's actually going to be the test for us to see whether or not a differential equation is exact. So let's let m and n be defined as they are before. Suppose they're defined on a rectangle where x ranges from a to b and c ranges from c to d. Then a necessary and sufficient condition for the differential to be exact is that we would need the partial of m with respect to y to be equal to the partial of n with respect to x. The way I always kind of memorize this test is, in particular, if I'm looking at m, I know m is with the dx term, so I wanted to take its partial with respect to the other variable. So we're taking the partial of m with respect to y. Similarly, n is being multiplied by dy, so I want to take its partial with respect to the other variable, which would be the x, so partial n, partial x. And if those two partial derivatives are equal to each other, then that's what it means for the differential equation to be exact. Now, from there, what can we do if we know that it's exact? So how are we actually going to solve these? Well, in particular, if we know that this is a exact differential, then what that means is that this function m of x comma y, that was actually the partial of f with respect to x. And similarly, that would have also have told us that n was the partial of f with respect to y. So if we take the function m of x comma y, and if we integrate that with respect to dx, then that will give us the original function f of x comma y up to a constant of integration. Now recall, if you're integrating a function of x and y dx, the constant of integration in that context is actually a function of y, because any y term with the derivative with respect to x would have been 0. So when you integrate dx, we get a constant function y. We will then be able to recover that constant function y by doing the following thing. If we now take this new expression for f, and if we take its partial with respect to y, well, the partial of f with respect to y, remember, that's what n of x comma y was. So we simply set that expression equal to n of x comma y, and that will give us an expression to solve for the derivative g prime, and then simple integration will allow us to get the original function g back. Again, the notation that looks, wildly crazy all over here, a lot of things. Don't memorize these individual little formulas. Just go through the process each time, and it's really not too bad. Let's take a look at our first one together. Suppose we were asked to solve 2xy dx plus x squared minus 1 dy. Again, this would be one that's actually separable, so we could have solved it via a number of different approaches. But let's solve it and try to see if it's an exact differential. So starting off, the function m in this case. So m of x comma y, that's the coefficient of dx, that's 2xy. The n of x comma y, that's the coefficient of y, that's x squared minus 1. And then what we want to check is we need to look at the partial of m with respect to y. So if I differentiate this expression with respect to y, holding the x constant, so we would simply get 2x times 1, or 2x. We would then need to take the partial of n with respect to x. So if I differentiate this function with respect to x, we get 2x. And then what that tells us is that these two partials are equal to each other. The partial of m with respect to y is equal to the partial of n with respect to x. They were both commonly equal to 2x, which means that this is going to be an exact differential. So in this case, there is some function, f of x comma y, this is exactly what this means, such that its differential is equal to 2xy dx plus y squared, x squared, sorry. X squared minus 1 dy. And we know that the form of a differential looks like this. It's partial f, partial x dx, plus partial y, partial f, sorry, partial y dy. So that tells us that our m of x comma y, let's come back up here. So we know that the partial of f with respect to x, that's equal to m of x comma y, which is 2xy. And similarly, the partial of f with respect to y, that would be this x squared minus 1 term. So now what do we do from here? Well, we're going to integrate. So if I wanted to recover the original function f, we would need to undo a derivative with respect to x. And the way you undo a derivative with respect to x is you integrate with respect to x. So I'm going to integrate both sides of this equation dx. Again, the antiderivative and the derivative cancel. So this would return f of x comma y is equal to, again, with respect to x, we treat the y as constant. The antiderivative of 2x is x squared y plus our constant of integration. Now, if the integration is done dx, then we would get some function of y as our constant of integration. And now, in order to solve that y, for g of y, what we're going to do is we're now going to take this expression, we integrate it with respect to x, we're now going to differentiate it with respect to y. So if we do the partial of f, actually let me just rewrite it real quickly. It's a color change issue kind of day. There we go. So I'm now going to take my last expression we had here, and we're going to take the partial with respect to y. So the partial of f with respect to y so partial f partial y. If I do the derivative of this thing with respect to y, that's going to give us x squared plus g prime of y. But remember, the partial of f with respect to y, that's simply equal to n of x. So here's what we know. We know that x squared minus 1 is supposed to be equal to x squared plus g prime of y. And now simply solve this equation for g prime of y. I could subtract x squared from both sides. This cancels. This would give us that negative 1 is equal to g prime of y. This is just a simple derivative of a single variable. So then to find g of y, all we have to do is integrate. So g of y, just integrate both sides of this. And we find that g of y is going to be equal to negative y plus some constant. And that gives us our solution. So f of x comma y, this is equal to, we had, if we go back down here, we had x squared y plus g of y, but we know that g of y is going to be just negative y plus c. And we know that this whole thing was actually equal to 0, so what we can do is we can actually go a little bit further by explicitly solving this for y. So the explicit form of the solution, because remember, if you were to integrate the right-hand side, that would have just simply given us 0. So we have x squared y minus y plus c equals to 0. And let's go ahead and get y by itself. We can factor out the y. move the c over. It's just going to be some other constant. And then this will be x squared minus 1. Divide both sides by x squared minus 1. And we get y equals c divided by x squared minus 1. And of course, this would be defined on any interval not containing plus or minus 1.